Hello everyone. Today I will talk about mathematical relations. We need this topic to have better understanding about graphs, which I will start talking about it from the next week. So what do we mean by relations in mathematics? We can define it by using sets. So if you consider A, B, C as elements in one set and X, Y, Z from another set, we can show relation between them by using these edges. So we have different types of relations in mathematics, and we can talk about them one by one, and they have various properties, and based on that we can define terms such as graphs, which we will talk about next week. So one of them is binary relation. Let A and B be sets, so we are talking about two sets. A binary relation from A to B is a subset of A multiply B. This is a Cartesian product. You're already familiar with this Cartesian product, and we are talking about a subset of it. This is very important to notice. So first, if you want to know what are the elements of this product, you can multiply these two together. You already know how to do that. And we can define various relations inside this new set as subsets of this one. So in other words, a binary relation from A to B is a set R of ordered pairs where the first element of each ordered pair comes from A and the second element comes from B. We already know about Cartesian product, so we know that at the end we will have pairs like this. So we have a tuple containing two elements. The order matters. In sets, as we mentioned before, the elements doesn't matter. For example, the order, it can be, for example, first or second, or we can have frequency of them. It doesn't matter. But when we talk about tuples, like pair, then of course a pair, for example, AB is different from BA, and we should be careful about that. So now that we define relation, we use the notation A related to B to denote that this pair belongs to this set. What is this set? This is a subset of A multiply B. Okay, and if this pair doesn't belong to R, then we can show it also like this, that you have a line on it to show that these two are not related to one another. Moreover, when this pair belongs to R, A is said to be related to B by R, as we mentioned before. Now look at this example. We have two sets, A and B, each one of them containing elements, like for example, A contains these three elements, B these two, and this set is a subset of the Cartesian product of these two. What's the size of the Cartesian product of these two? Can you say that? The size of A is 3, the size of B is 2, so their multiplication is 6. So the Cartesian product should have 6 elements inside it. But this set contains 4 elements because this one is a subset of that. So this one we can define it as a relation, and on the graph you can also see that we have such a case that A0 is related to A and 0 is also related to B. When we have an arrow, it means that 0 is related to A, but not A is related to 0. We should be careful about these things too, especially in graphs, and we will talk about it in details next week. Also, we can define tables for them, such a thing, for example, to show if they are related to one another or not. But the problem with this table is that at the same time it shows that A is also related to 0. So this picture doesn't represent it perfectly in that sense. But as I said, this is important in graphs more than relation, but in some examples that I will mention it, it can be important as well. Okay, sometimes we can also define such relations from one set to itself. And you know that we can also define it as subset of this Cartesian product. And what do we mean by reflexive relation? A relation R on a set A is called reflexive if this pair AA, which belongs to R, for every element A belongs to A. So it means that at the same time, if you see an element in A, doesn't matter which element because it says for every element. For the second component, for the second element in the pair, we should have the same number as well. If we don't have such a case, that set, well, we cannot consider it as a reflexive relation. Take a look at this example to see what do we mean by that. And it says that the relations R3 and R5 are reflexive because they both contain all pairs of the form AA, and it named them. So in this example, we have a set, and based on that, we can have for example, A multiply A case. Let me show you like this. A multiply A Cartesian product, and you can write different relations as subsets of that set, okay? So of course we will have such pairs. What's the size of A multiply A? This is 16, because A, if I consider this one as A, this one contains 4 elements, then 4 multiply 4 is 16. Now we can define different subsets of them. You see, all of them are subsets of that big set. This is the size of it. Okay. Now here it says that R3 and R5 are reflexive. Why is that? Because if I see, for example, 1, here if I see 1, again I should see 1 inside the same set. If it has 1 and 2, it doesn't matter as long as you can find in the same set such a pair. As soon as you see 2, you should find 2, and in the second component 2 as well. Here you can find it, you see? So first check the first element. If you see, for example, 3, you should have 3 here or in another pair. Otherwise, it will be problematic. For example, why R2 is not reflexive? 1, 1 is okay, but what about this one? 2, 1. We don't have any 2, 2 pair inside this set. So this relation is not reflexive. You see? Why R1 is not reflexive? Because I see 3, 4, but I don't see 3, 3 inside the same set. I think you got the idea. Now here also for R5, this is reflexive because whenever you see, for example, 1, you also have 1, 1 inside the same set. It's very easy to detect them. What about these two properties, symmetric and antisymmetric? A relation R on a set A is called symmetric if BA belongs to R whenever AB belongs to R. So if we have such a pair inside this relation as an element, the whole thing here is just one element, right? This is defined as a pair. So if you have BA, for sure you should have AB inside the same set. Otherwise, we don't call it symmetric. And a relation R on a set A such that for all AB belongs to A, if AB belongs to R and BA belongs to R, we have no other choice to make them equal. Otherwise, this is not antisymmetric. We can talk about it too now, also in the same example. Now, the relations R2 and R3 are symmetric. Let's see why. R2 is symmetric because whenever you see, for example, one element here, for the second element, you should find it as well. For example, you have AA or 1, 1. For sure, you will have 1, 1 again. So for a set, you know we don't repeat it. So that's it, the same thing. Here we have 1, 2. So for sure, we should have 2, 1. Okay, you just interchange 1 and 2 as the first and second component, right? So let's take a look at this one, R6. R6 is not symmetric. Why is that? Because we don't have 4, 3 inside this set. So this one is not symmetric. Now, it's talking about that. Let's see what about antisymmetric. It says R4, R5, and R6 are all antisymmetric. Why is that? Okay, here, for example, in R6, if we have 3, 4, we shouldn't have 4, 3. That's the case. If it happens, 3 should be exactly equal to 3, and 4 should be equal to 3. What do we mean by that? For example, here, 1, 2. If we have 1, 2, we can't have 2, 1 inside this set. This is the property of antisymmetry. If we have, this is not antisymmetry anymore. You check and there is none. Again, for all of them, we should check. There is only one case which can have such a case. Like 1, 1, if we interchange their places, again, it will be 1, 1. It is allowed inside the antisymmetric property. That's what we mean when we say they have no other choice to be equal, otherwise it's not possible. So in cases when they are different, the first and second component inside the pair, then we shouldn't have that element inside. Like, for example, R1. Let's check for this one. When I have 1, 2, I shouldn't have 2, 1, but I have here. So it means that this is not antisymmetric. You see? For 1, 2, again, I have 2, 1. This is not antisymmetric. For R3, why this one is not antisymmetric? Again, I see 1, 2, and 2, 1. I see 1, 4, 4, 1. So again, this is not antisymmetric. As soon as you find one counterexample, that's good enough to say this set is not antisymmetric. Okay, let's go through another a topic related to relations. So, transitive relation. What type of relation is that? A relation R on set A is called transitive if whenever AB as a pair belongs to R and BC also belongs to R, this one should be also belongs to R. So AC also belongs to R. Here, look at this one. B in the second component and B in the first component, they are the same. So if such a case happens, AC also should be inside the same relation as a set as well. And for all ABC inside A, this holds. So let's see, and actually we can show it in another example because it's pretty easy, you understand it, right? Like just here I can give an example. Like if 1, 2 belongs to R1, for example, and also we know that 2, 3 belongs to R1, if we claim that this relation R1 is transitive, then for sure 1, 3 should belong to the same relation as well. Okay, this is the idea of this transitive relation, and we will practice it together. So what about combining relations? Because relations from A to B are subset of A multiply B as a Cartesian product, we know. So two relations from A to B can be combined. Anyway, two sets can be combined. So exactly the same way it happens. Like if we have A as these elements and B as these elements, the two sets, the relations R1 and R2 are defined in A multiply B, right? They define as subset of this one. A contains only values like this, single values B2, but here for R1 and R2, as you see, we have pairs of elements. So these ones can be combined by using the same operations as we use inside sets. So if you know how to deal with them, of course, you know how to deal with these relations as well. Nothing different. So the logic is exactly the same. What about composite of relations? So let R be a relation from a set A to B, and S a relation from B to C. Okay, so we define two relations, one from A to B, another relation from B to C. We are dealing with three different sets now. The composite of R and S is the relation consisting of order pairs AC, where A belongs to A and C belongs to C, and for which there exists an element B. This is the common element, such that AB belongs to R and BC belongs to C. That's why I call it the common element. For matrices, when we wanted to multiply them, we check the size like this, so that the multiplication can be possible. This is the same logic. Can you see that? So we should have such a case in order to be able to define composite of relation. So we denote composite of R and S by SOR, something like this. And be careful, we say composite of R and S, but we show it SOR, S before R, although we say R here first. I show it in the example why this is important, because ROS is different from SOR. The composite of functions was the same situation as well. Like if we had two functions, not necessarily these two were equal. That's why we should be careful about the order of them. And by the way, now that I talked about the functions, you know, when I say fgx, it means that you insert this one inside the function and find it. So and the definition is like that. First, we consider this one and this one. This is the same situation. When I say composite of R and S, you write S first, okay? Now, as an example, what's the composite of the relations R and S, where R is the relation from this set to this one, so this one is R, and with, this is defined like this. So as a subset of A to B. Okay, so not the whole thing, like we don't have the whole thing as A multiply B, as a subset of that. And R is a subset of that, as you can see. And S is the relation from this one to this one. Okay, this one belongs to S, and we define S like this. Okay. Now, SOR is constructed using all order pairs in R and order pairs in S, where the second element of the order pair in R agrees with the first element of the order pair in S. So, when I say SOR, this is the part that we should be careful about. It means that first check for R. Here I have 1, 1. Check the second component of R. And then check the first component of S. If we have any common numbers, any common values, then that one can be a new element inside my SOR. So here I look for the first components only. Which one is 1? This is the one. So these two are the same. So what is left? This is 1, 0. You see, you find the common ones, you eliminate them. Now you have 1, 0. The same situation that we had for matrices. When you have 3 by 2 matrix and you multiply it by 2 by 3, this multiplication is possible because they have these common sizes here. This is the column of the first matrix. This is the row of the second matrix. Of course, I'm talking about in terms of the size. And then the result would be a 3 by 3 matrix, right? This is the same logic. So that's the reason here I will have 1, 0. Let's practice with the rest of them. Now I have 1, 4. So let me check whether we have another one. Yes, we have here. So what is left is 1, 1. You see? 1, 1. That's why I will have 1, 1 here. Okay, next one, 2, 3. Do I have 3? Yes, 2 of them. So it means that I will have 2, 1 and 2, 2. See? And for the rest of them, you can do the same logic. 3, 1, again, you will have 1 here. So you will have 3, 0. Here for 3, 4, we have 4, 1. So you will have 3, 1. You see? So that's the composite of two relations. It's very easy, but it needs practice, because if we underestimate such things, maybe we don't pay attention to the order of SOR, that should I consider the second component of R or S? These things need a little practice, and I'm sure they are very easy to deal with. Now, it's also possible to compose the same relation to itself. And for that, we use power. So when you write a relation and you use power for that, it doesn't mean multiplication, okay? We should be careful about it. N times. So this is not the case. We don't consider this. So when you say Rn, it means that the composition. So here I have R power 1, it means that R itself. If I'm talking about R power n plus 1, it means that the relation, the composite relation between Rn and R, okay? The same way we are dealing with powers, we can also represent them. It's not a bad idea to show an example related to that. So if I consider R as this one, and we don't care, for example, what was A exactly, what was B, so that what's the subset of A multiply B. We are just talking about this relation. It's already defined for us. So if we have this relation, find the powers Rn from starting from 2 going to infinity. You would think, how can I deal with it? Because I cannot write the solution infinite times. So whenever we are dealing with such questions, it means that you will find a trend. If you find a trend, it means that starting from a point, you can define Rn exactly the same way as the previous relations. So let's see in this example. For example, for R2, if I apply the same composition rules as we did for this example, it means that you can write another set of R, 1, 1, 2, 1, 3, 2, and 4, 2, 4, 3, and then exactly apply the same way as you did for the previous one. And now order doesn't matter, because both of them are the same anyway. So you can choose, for example, this second component and this first one, and continue. So when you do that, R2 will be like this. So you should check from this point whether R power 2 is different from the previous set or not. Is R equal to R power 2 or not? This is not the case, okay? So we have two different sets. Why we do that? Because sometimes we can find the trend, and that's the final answer for all of the possible values for n. But unfortunately, it wasn't. So we should continue. So when you write R3. We should be careful. Here, R2 becomes, you write R2 before R, you see? And when you do that, this is the same story as SOR. It means that consider the second component of this one, okay? Not this one. We should be careful about these things from now. So consider the second component of this one and then the first component of this, and you can come up with R power 3 the same way you did for SOR. Okay, when you reach this set R3, compare it with the previous sets. Do we have the same sets or not? No, we don't. R3 is not the same as the previous sets. But when we continue like this, and we find, for example, R4 after that, then, well, by the way, how can you come up with R4? You can say, for example, this is R3, R, and you find R4, for example. You can also do that, R2, R2. They should give you the same answer. Anyway, now when you find about the answer for R4, you compare it with the previous one. You should check these ones. Is R4 equal to R1 or not? Is R4 equal to R2 or not? What about R4 to R3? Okay, let's check. For the first one, no. It is not equal to this one. This is not equal to R2, but this is equal to R3, you see? And if you try to come up with R power 5, by the way, when I write R4 like this, I mean R power. Okay, write it above it so that we know this is power. Like this. I named them, but actually I mean power. Okay, so when I talk about R5, again, R5 will be exactly the same as R4, which was exactly the same as R3. So what do I understand from here? I understand that there is a trend. So there is a trend here, and I understand starting from the value 3 until infinity, I will have exactly the same elements in my relations, okay? So again, also from 5, 6, 7 to infinity, this is the same story. So what should I do in terms of the final answer? In the final answer, you write the elements of R here, like this. Then you write the elements of R power 2. Then you write Rn, and you define it, and you say this one holds from n starting from 3. But in order to be specific exactly, we are not talking about real numbers or integers. You can say that n belongs to natural numbers. This is one way. Another way is to show it like this. N equal to 3, 4, going to infinity. Okay, it depends on you which one you prefer. At the same time, you should write this for this n, or you can write like this to specify exactly from which point we have the same set as we define relation. Okay, guys, it was the introduction related to relations, and we need this because we need to talk about graphs in the next session. Next session, actually, we will have, yes, it will be 1st of January, so there won't be online session, but I will record a video for the topic related to graphs, and I will post it on O2 class. Please go through chapter 9, the first section, and go through the examples. There are so many examples related to relations which can be useful. We will also practice them together in the weekly assignment. So if you have any questions, please let me know. Otherwise, I will see you guys on next Wednesday.